were talking about space quantization, and we said that the angular momentum vector can have only certain values, and then of course, it can have only certain orientations. In fact, in the case where L is equal to 1, you saw that there are only 3 possible orientations, they have different values for the z component of the angular momentum vector. But then you see many times this can leave you slightly confused, what is so special about z axis, right. I mean, there is nothing special about z axis. If you want, you can take z axis the way you want, in whichever direction you want. So, actually the way we have solved the Schrodinger equation, the solutions that we obtained were such that, right, the z component, the answers that we obtained were such that the z component of the angular momentum had certain values. That is what happened. Now, actually if you remember, you see in my definition of polar coordinates, the z axis was kind of special. It was special in the sense that we measured theta from the z axis. But suppose I decide to say, okay, I will define a new polar coordinate such that theta is measured from the x axis, then the solutions that I would have obtained would have had the x component of the angular momentum having quantized values like m h cross. So, therefore, do not be under the impression that z axis has anything special. It is just the way we did the things, z axis was special, and so the solutions were like that. That is the first thing. The second thing is, I mean, it is nice to say, oh, there is all this quantization, but what is the proof? I mean, ultimately you should never believe what a theoretician, I am a theoretician, but so you should never believe what a theoretician tells you unless you have experimental evidence. Without experimental evidence, you do not believe anything. Ultimately, anything that any theory has to agree with experiments. So, therefore, it should be possible for me to demonstrate to you that this quantization actually exists, not enough just to say that the quantization is there. So, let me give you an experiment which can in principle be used, though in practice what happens is that the answers that you get will necessitate the modifying of the theory. Actually, the experiment when performed will require that the theory that I had been telling you should be modified. We will see. Okay, let again, whenever we think of new things, always we will ask what will happen if the system obey classical mechanics and then come back to quantum mechanics. So, imagine I have this electron which is going around the nucleus in a perfect circular orbit, right. In the Bohr theory, as I told you, this is a planar orbit, it is flat in one plane and it will be moving with a velocity v along a circle of radius r. And if you remember your Bohr theory, what will happen is that the theory will tell you that there is an angular momentum whose magnitude actually equal to mass into velocity into r. Not that I have written only L, not vector, because I am only concerned with the magnitude at the moment, correct. And now you see the electron is a charged particle. So, this is actually a charged particle going in a circle, that actually is a current, right. And so, you have a current going in a closed loop, and if that happens, there will always be a magnetic moment. So, if I wanted to calculate the magnitude of the magnetic moment, I can use a formula. The magnitude of the magnetic moment will be nothing but the current multiplied by the area of the loop. If I have a circular loop and then if there is a steady current going around it, the magnitude of the current is I and the area of this loop is equal to A, then the magnetic moment that the system would have is I into A. So, what is the area even for this kind of circular orbit? Area will be pi r square, correct. And I want to calculate the current. So, you have the electron, it is moving with a velocity v, right. So, how many times will the electron go around in unit time? Well, for a circular orbit, of course, the perimeter or the circumference is 2 pi r. So, therefore, if the electron is moving with a velocity v, then it will go around the orbit so many times in 1 second, right. Velocity is the distance that it will cover in unit time, and 2 pi r is the circumference. So, therefore, so many number of times the electron is going to go around, and the electron has a charge, right. At the moment, let me write just an E, but of course, it is negative. I will come to that. I will modify this E and put minus E, right. So, therefore, so many times the electron is going around it, and therefore, the current actually is so much. Current is charge going per unit time, right. So, therefore, current is so much and the area is so much. So, therefore, what will be the magnitude of the magnetic moment? Actually, you will have E into V divided by 2 pi r. How much is that? R and R are going to cancel, pi and pi are going to cancel. So, I will be left with E. Let me put there is a 2 here, let me put an m in the denominators, which means that I will have to put an m in the numerator. So, I will get mvr. Correct? Why should I have mvr? Well, we want mvr because that is the angular momentum. That is why I included that m. And therefore, the magnitude of the magnetic moment is nothing but E divided by 2 m into L, where L is the magnitude of the angular momentum. This is of course classical, right. Now, if I was going to think about it quantum mechanically, what will happen? I can say, okay, or I mean, let me before I go into quantum mechanics, I want to modify this because you see these things mu as well as L are vectors. So, therefore, what will happen? I will have mu equal to, well, you see, if I had a charge which is going in this direction like that, or maybe like to be very clear, let me say I have the circular orbit, a charge E is going around it. For the moment, imagine it is positive, then if it is going around it, then what will happen is that the angular momentum is a vector pointing towards you, if it is following that orbit in the direction that I am showing in with my hand, and the magnetic moment also will be in the same direction. But now I say, okay, the charge is actually, because I am thinking of the electron, the charge is negative, then what will happen? The angular momentum vector will be still in this direction, but the magnetic moment will be in the opposite direction, because the charge is negative, and therefore, what is the expression that I would have? I would have mu equal to minus E divided by 2 m and vector L. So, this is the precise relationship between angular momentum and magnetic moment of the electron. So, therefore, I mean, why do we think of this? The answer is that if you had the electron sitting in this any of these stationary states, it is likely that it will have a magnetic moment, because the magnetic moment is related to the angular momentum vector, right. For example, if you think of the s orbital, what do you expect? For the s orbital, the magnitude of the angular momentum vector, I did not discuss this simply because it was 0, right. The quantum number L is 0, therefore, magnitude of the angular momentum vector is 0. So, it has no angular momentum vector, actually it is 0, and therefore, the magnetic moment also is 0. But if you had L equal to 1, what will happen? L equal to 1 means the magnetic moment. If you calculate the magnitude of the magnetic moment, you know precisely how much it is. It is going to be mu magnitude, and that will be equal to E divided by 2 m magnitude of L, and that actually is going to be E divided by 2 m square root of L into L plus 1 h cross square. This is what is going to happen if you think of the magnitude of the magnetic moment. But because L has 3 different orientations now, the magnetic moment also has 3 different orientations. Now, can I do an experiment which actually will demonstrate these 3 orientations? And only if I can do that, should I believe in all this stuff that quantum mechanics is telling me, right? I have to be able to verify this experimentally. So, how will I verify this experimentally is the question that I am going to ask. So, let me imagine I have here a beam of hydrogen atoms. I should tell you that this is a very, very difficult experiment. And in fact, I do not know whether this particular experiment has ever been done. Maybe it is done, I mean, because these days people have done almost everything that can be done. This kind of experiment was originally done with silver atoms. We will come to that in a few minutes. But let us imagine that I have a beam of hydrogen atoms, and I will prepare them in the state with L equal to 1. Okay, suppose I can prepare them in the state with L equal to 1. That actually means, I mean, because you would have a little bit of familiarity with the spectroscopy. What you do is you take hydrogen atom, expose it to radiation of the correct frequency, so that the hydrogen atom makes a transition from the 1s orbital to the 2p orbital. That is all. Or it is not necessary that it should be 2p, it may be 3p. You can make a transition, and that is all that you need to do in principle. So, suppose I have made these hydrogen atoms in the L equal to 1 state. So, what will happen? You see, they are all having a non-zero value for the angular momentum vector. That means they all would have, I mean, I would expect all of them to have a tiny magnetic moment. So, they are all tiny magnets, and the magnets are not having random orientations in space. I mean, suppose I now say, okay, I am going to apply a magnetic field. Okay, by having these 2 poles of a magnet, right? Then what will happen? These hydrogen atoms, they are actually tiny magnets. Okay, I can perhaps represent one hydrogen atom's magnetic moment by this. This is the north, and that is the south. Okay. And so, what will happen? This is the magnetic moment that it would have. Not only the magnetic moment, it would also have, right, an angular momentum, because L is equal to 1, and both actually are in the same direction, right. In that direction, of course, you see magnetic moment, if it is in this direction, the angular momentum will be in the opposite direction. So, if you say that there is a magnetic moment for this atom, what will happen? This magnetic field is going to act upon the magnet, you see, I mean, they have a tiny magnet, and it is put in a magnetic field. So, what will it try to do? It will, I mean, we all know, we have all played with magnets, experiencing the Earth's magnetic field, it will actually try to tilt. But the system has an angular momentum, and if the system has an angular momentum, actually this is very interesting, it is like a spinning top. If the system experiences a torque, what do I mean by a torque? You see, there is a force acting at this end, maybe trying to move it in this direction. There is a force acting on this other end in the opposite direction. So, therefore, that is what I refer to as a torque, that actually should tilt it in this fashion, but because this system has an angular momentum, it does not actually tilt, but instead it undergoes what is referred to as a precessional motion. You should be familiar with this. I have it on my computer. So, here is the precessional motion of a spinning top. So, what will happen is that, let me repeat, here is my magnet, there is an angular momentum associated with this magnet, right, and then you apply a torque trying to tilt the direction of the magnet, but the magnet actually it does not tilt, but instead it undergoes precessional motion, right, that is what it does. And further there is a force acting on this, let me say in this direction, another force acting on this in that direction, the two forces are actually equal but opposite in direction. So, that the net force acting on the magnet trying to move it from this position is 0, it is only trying to tilt it, it is not actually causing the center of mass of the magnet to move, because this force and that force actually are exactly equal. So, if I short a beam of hydrogen atoms, what will happen? They will actually simply pass through, because you see they may undergo this precessional motion for some time and then come out, that is all, right. That is the case if the magnetic field is uniform everywhere, but suppose the magnetic field was not uniform. How can you make it non-uniform? The answer is you see you have special kinds of magnets, maybe something like that. I think I have a pictures. Okay, you can see that the top pole of the magnet is constructed differently, and why do we do that? The answer is that if you had such a shape, the magnetic field is not uniform everywhere, it is going to be varying from point to point, and if it is varying from point to point, what will happen? The force that is exerted at this end and the force that is exerted at the other end are not going to be the same, and therefore, there will be a net force, and that will cause a displacement of this magnet maybe in the upward direction or maybe in the downward direction, depending upon how the magnet is oriented, right. Depending upon how the magnet is oriented, it may be displaced in the upward direction or in the downward direction. And now imagine, you see, I am going to have a large number of these magnets, their orientations in space are in different directions. If I short them and applied this inhomogeneous magnetic field, what will happen? Some of them will go down, some of them will go up, and many of them, it simply depends upon the orientation that the tiny magnets have, and therefore, what you would expect is that if I had a detector here, I would find it right arriving at different locations along my screen. But if the orientation that this magnet can have is special, what will happen? In fact, we have seen that because of the angular momentum vector, there are only 3 possible orientations when L is equal to 1. So, therefore, there are only 3 possible ways the magnet can be oriented with respect to the z direction. This is now my z direction. Notice that I have made the z direction special by putting a magnetic field in that direction. So, therefore, what would happen is that my tiny magnets can have only 3 kinds of orientations with respect to that direction, provided L is equal to 1. And so, what would you expect? Your beam of hydrogen atoms which go through the magnetic field, they will be split up into 3, right. That is what is shown in this picture. So, this is what you would expect, and therefore, this is actually a very clear experimental verification of the space quantization that I was talking about. You can imagine doing the same experiment with L equal to 2, you will find that the beam will be split up into 5. Okay. So, everything seems to be nice, but unfortunately, this experiment, if you did it this way, let us say I will do it with hydrogen atoms in the ground state, the electrons are in the all in the 1s atomic orbital. What would you expect to happen if it is in the 1s? Angular momentum vector is 0, so you do not expect the beam to be split up. But if you did the experiment, you will find that it is split up into 2. As I said, this kind of experiment is extremely difficult to do with hydrogen atoms, because you see hydrogen atoms, they do not exist free, it is difficult to make them. You have to start with hydrogen molecule, dissociate it, then accelerate the whole thing, or do something to get hydrogen atoms, but silver atoms are very easy. Silver atoms, you just evaporate silver, they will come out. It was actually done by Stern and Gerlach long ago. And they used a beam of silver atoms, and it was found that the beam split into 2, and they had no explanation for this, and an explanation was actually given by Uhlenbeck and Goudsmit. The way silver atom is, you see, you have a closed shell and with one electron sitting outside, and that electron is sitting in an s orbital. The closed shell has no angular momentum, net angular momentum is 0. The electron that is sitting outside, you do not expect it to have an angular momentum, because it is sitting in an s orbital. And when they did this experiment with silver atoms, I mean, they didn't know quantum mechanics at that time, because quantum mechanics was yet to be completely developed. They did this experiment and found that the beam actually splits up into 2, and therefore, there is something that we have not yet discussed, and what leads to this? The answer is that an electron in hydrogen atom sitting in a 1s orbital, it has a magnetic moment, even though we did not expect one due to its orbital motion. It was going around the nucleus, but that there was no angular momentum, but the electron does have an angular momentum. And not only that, I mean, when I say how do I know that it has an angular momentum, I say that because I have found that there is a magnetic moment. This experiment only shows you that there is a magnetic moment. So, therefore, there is an angular momentum, and that angular momentum can have 2 orientations in space. And to explain this, the idea of a spin was suggested. So, if you like, you can imagine, at least in those days, this is what people did at first. You imagine that the electron is something like a sphere. This is not a correct picture. Before I even introduce the picture, I want to say that this is not the way one has to think of spin, but this is helpful. Imagine it is a sphere having a finite size, and imagine that it is spinning about such an axis. So, the electron has a negative charge. So, if it is spinning, that actually means the charge is actually going around, that means it is there is an angular momentum, there is also a magnetic moment. And the angular momentum associated with this, we will call it spin angular momentum, and we will denote it by the symbol S with a line on top of it. But as is usual in quantum mechanics, you see, whenever you say you have a quantity, you have to think of the operator. So, therefore, we will have a spin operator, which is a vector operator, just like your angular momentum operators that occurred. When I say that angular momentum operator, those operators, they are referred to as orbital angular momentum operators, because they were concerned with orbital motion. Now, I am thinking of spinning motion, where you can imagine you have a ball which is just spinning, and I am sure you are all familiar with spinning of balls, you all play cricket definitely. So, therefore, spinning, and the spinning leads to an angular momentum, and because the electron is charged, it also leads to a magnetic moment. And you can expect that the spin angular momentum is related to the magnetic moment, right. This is what happened with orbital angular momentum. So, what would you expect if I just use the same expression as earlier, I would have obtained minus E by 2 m times. Yes, this is what happened with orbital angular momentum, but interestingly this formula is not correct for the electron. You have to multiply this actually by a factor which is 2 almost, actually 2 point not some 18 or something. Let us not worry about that, it is equal to 2 for our purpose. And further what is happening is that this spin has only 2 possible orientations, right. So, what does that mean? It means that the following, you see, you look at an angular momentum vector having an L quantum number, having an azimuthal quantum number equal to L, then the magnitude of the angular momentum vector is square root of L into L plus 1 into H cross square, that is what the magnitude is. And then this has how many different orientations? The different orientations correspond to m being 0, plus or minus 1, plus or minus 2, plus or minus 3, etc., until plus or minus L. So, if the quantum number is L, then there are 2 L plus 1 different orientations, right. For example, if L is equal to 1, there are 3 different orientations, if L is equal to 2, there are 5 different orientations. Now, here what we are finding is that experimentally we are finding that there are only 2 orientations. So, how can we bring that into the same kind of framework, right? The answer is to say that okay, there is a quantum number similar to this L, but somewhat different. I will tell you why it is different. I am going to denote that quantum number by S. That the quantum number L could take any value from 0, 1, 2, 3, etc., up to infinity, but this S quantum number I am going to say that it can have only the value half. And not only that, it can be oriented such that its Z component is ms times h cross, with ms being plus half or minus half. These are the only 2 possibilities. Why do I say that? Because that is what the experiment says, right, because the experiment shows that there are only 2 possible orientations, right. So, therefore, I will say that okay, there are only 2 possible orientations. See, if you had a general value for L, the number of orientations would be 2L plus 1, right. So, if you put instead of L, if you put half there, then you would realize that there are 2 possible orientations only. So, it is as if this quantum number L is taking the value half, and we do not call it L anymore, because we are not concerned with orbital motion, but we are concerned with spin motion. So, we call it S. So, therefore, the way we are going to work now is to say that okay, this experiment demonstrates that there is something like the spin with it has an angular momentum associated with it, and it has a quantum number S is equal to half. This will specify the magnitude of the angular momentum vector, which will be equal to square root of S into S plus 1 H cross, right, just like what you have there. The only thing is instead of L you will have to put S, but there L will take values, different values 0, 1, 2, 3, etc., but here S is confined, it can have only one value equal to half, and hence the magnitude of the angle of the spin angular momentum vector will be square root of half into half plus 1 H cross. And there are 2 possible orientations. Now, again if you look at this case, the angular momentum case, you have functions like psi 210, psi 21 plus 1, psi 21 minus 1, they have different values for m. These functions have different values for m, but the values of L are the same, right. So, similarly you can say, okay, what I should imagine is that I have a state where S is equal to half and ms is equal to plus half. This is one possible state in which the spin of the electron can be. The spin of the electron is oriented in such a fashion that the z component of the spin angular momentum is plus half times h cross. That is one possible state of the electron, and there is another possible state of the electron in which the spin is oriented in a different fashion, and that state would have ms equal to minus half. Now, you see these are all just written down using intuition to explain the experiment. Well, this definitely is unsatisfactory if you are a pure theoretician, because you see, I mean, you want to understand the thing, not just assume something. So, so the way one can actually derive these things is as follows. See, till now we were discussing what is referred to as the Schrodinger equation. The Schrodinger equation has the defect that it does not worry about relativity theory at all, okay. But you have to actually include relativity theory if you want to describe the natural world in the correct fashion, and if you included relativity theory, actually what you will have to do is you will have to formulate an equation which was originally formulated by Dirac. This properly takes relativity theory into account, and if you solved the Dirac equation, the spin will automatically come out of the solution. Right. We are handling the non-relativistic equation known as the Schrodinger equation, and by solving that, what happened, we got only 3 quantum numbers, we did not get the 4th quantum number. If you want to get the 4th quantum number, you have to do a very detailed derivation using an equation which is referred to as the Dirac equation, and we will not do that, because you see chemists are not terribly interested in the Dirac equation. Of course, they are interested in the spin. So, therefore, what is normally done is to introduce a spin as an assumption. That is what chemists would normally do, and that is all that we are going to do. We are not going to go into Dirac equation. So, therefore, we now have this, I mean, if you say, you can say this is an additional postulate of quantum mechanics for the chemists, right. The additional postulate being that the electron has a spin associated with which it has a spin angular momentum. This spin angular momentum has only a certain magnitude. The magnitude is actually, let me write it down, I have not written it down anywhere. Magnitude is actually square root of half into half plus 1 h cross is the magnitude of the spin angular momentum vector, and the spin has 2 orientations characterized by different values of ms, ms being either plus half or minus half, right, and corresponding to different values of the magnetic quantum number m for these functions. You had, each one had a different wave function. So, similarly, we will have to say that these 2 different states of the spin should have some spin wave function, right. Again, that has to be assumed. What we will do is, we will say that if ms is equal to plus half, there must be a wave function characterizing that state, and that I will denote as alpha, right. So, here the spin is oriented in a direction which is upward, such that the z component of the spin angular momentum is plus half h cross. So, we normally say that the spin is pointing up. So, that state we will denote by the symbol alpha, and if ms is equal to minus half, we will say that the state is going to be denoted as beta. So, we will say that the wave function or the statement, let me not say state function, the wave function for the electron will have an additional part. Up to now we had only psi n l m r theta phi. This was obtained from the Schrodinger equation, but now I am going to say that in addition to this the wave function has another part which I will denote by the symbol maybe alpha. This is actually the spin part, or maybe beta, but these things are actually this function is a function of r theta phi, okay. And so it is natural that this may be thought of as a function of something. You can say okay that something because this is all postulates that something is something that is not very clear, but we will say okay that is our spin coordinate and denote it by the symbol omega if you like, which you can say it is actually some coordinate which is connected with the orientation of spin, right. And similarly this other function, what will happen is that you will have beta of omega. So, if you think of the ground state wave function for hydrogen atom, the wave function would look like psi 1s equal to 1 by square root of pi a0 cube e to the power of minus r by a0, and this wave function does not contain spin. Now, if you added spin also to this function, what will happen is that you will have either alpha of omega, alpha is the spin wave function, omega is the spin coordinate, or we have the other possibility of having beta of omega. So, there are two possible states, two possible spin states being represented by the wave functions alpha of omega and beta of omega. So, there are two possible states for the electron. See, until now I had said that the ground state actually ground state of the hydrogen atom is non-degenerate, but when I take this into account, spin into account, it is no longer degenerate because the electron has a spin. The spin can be, the spin function can be either alpha or beta. So, therefore, there are two possible states. Now, it is doubly degenerate. Fine. And not only that, you can also introduce, see if you say that S is a vector, you can actually introduce operators corresponding to x component, y component and z component, okay. You can introduce them also, and then what will you do? You have to follow analogy with orbital angular momentum, because whenever you have an operator you will need to know what are the commutation relationships. So, you will say that okay Sx commutated with Sy should be equal to how much? It has to be equal to IH cross Sz, and similarly you have other commutation relationships, and if that is the way it is, what will happen? You will find that S square can be defined, S square will commute with Sx, Sy and Sz. Sx, Sy is Z among themselves they will not commute, and therefore, you can specify only the value of S square and if you like Sz. And further Sz operating upon alpha, what will it give me? Here you see alpha is the state where the electron's spin is pointing up, it is pointing up in such a fashion that the Z component is plus half times H cross. So, if Sz operates upon alpha, what I would expect is I would get half H cross times alpha, while if Sz operated upon beta, I will get minus half times H cross. And not only that, if S square operated upon alpha, here I mean alpha is an eigen function of S square with an eigen value which will be equal to how much? S into S plus 1 H cross square. into alpha, and that S is actually half into half plus 1. Right. So, this is how things are. So, you would realize that if you wanted to get spin, you have to take relativity theory into account, and if you did it properly, then of course, spin can be derived from what is referred to as the Dirac equation. So, therefore, strictly speaking, spin is a relativistic phenomenon, and this picture that I have drawn here, imagining that the electron is a hard sphere which is actually rotating, spinning about an axis, that is not the correct picture, but it is a useful picture if you are going to think about spin. It is useful, but it is not necessary that that will give you the correct results. Okay. Okay, I think I will stop here today. Thank you for listening.